Good morning. I would like to welcome here again for the second lecture in the guest lecture series. And today we will continue in the topic we started yesterday. The topic was Bayesian machine learning, and hopefully we will see or learn more interesting things.
Thank you. So today's lecture is going to be about different algorithms for doing inference, exact inference, and approximate inference in discrete graphical models. These are going to be probabilistic graphical models with discrete random variables. In the first lecture, we saw that we are going to use this model-based approach to machine learning, in which we were combining a probabilistic model that explains how the data is generated with some data, and we were using for this an inference algorithm that was going to make predictions. In this lecture, we will see an example of different inference algorithms. So let's start by defining what is inference. Inference can be understood as the task of computing a conditional distribution in a particular probabilistic graphical model once we have observed some of the value of some of the random variables in this model. So given that some of the random variables in a graphical model are fixed to some observed values, we want to compute the conditional distribution of a subset of other variables. The simplest example for this problem is the case in which we have a two-dimensional probability distribution specified in terms of a Bayesian network with this graphical model that specifies a factorization of the joint in terms of a product of the conditional distribution of y given x times the marginal distribution of x. This is the chain rule of Bayesian networks, which is for each node in the network we have that the joint probability is a product of a factor for each node in the network, where each factor is the conditional distribution of that node given the parents of that node in the network. We observe then the value of y in this graphical model. We denote that by shading the node of y, and then we can ask about the conditional distribution of x given y. We can obtain that conditional distribution using Bayes' theorem, which states that the joint is just the conditional distribution of x given y is just the joint divided by the marginal distribution of y, which is obtained by summing out x in the joint distribution. This is the sum rule. So, in general, the computation of these conditional probabilities will require us to compute some marginalizations of the joint distribution over a subset of random variables. Because we will have to sum across the states of a subset of random variables, we will have, in general, an exponential cost, which in the worst case. The reason for this is that we are summing across the states of a subset of random variables, and there are an exponential number of states for those random variables. However, we will see that for some probabilistic graphical models, we will be able to perform exact inference in a computationally efficient way by exploiting a structure in the joint distribution. The probabilistic graphical model is going to specify the joint distribution as a product of simple factors, and by operating with those simple factors that will depend only on a reduced set of random variables, we will be able to do inference in a computationally efficient way. So let's see a simple example of how can this be done. Let's assume we have this Bayesian network, A connected to B, connected to C, and connected to D. And let's assume we want to compute the marginal distribution of D. We want to sum out in the joint the variables A, B, and C. We can do this by making use of the chain rule to write the joint distribution, just by taking a product of a factor, one for each node in the network, given the value of the parent. Once we have the joint, we can sum out these variables A, B, and C. The problem is that this operation is going to be very expensive. In particular, we are expanding the joint distribution, which if we have discrete random variables, and each of these random variables can have n different states, the computational cost of doing this operation will scale as n to the 4th power. This is going to be the size of the representation of the joint in terms of a probability table. We have a table with as many entries as states of these variables, and we will have n to the 4th power different states. So this is very expensive, but it turns out that we can do this computation in a much more efficient way by just reordering the computations. Instead of computing the joint and summing across all these variables, what we are going to do is specify an ordering of for the sums of the variables. We have to sum across C, B, and A. We are going to specify an ordering for computing these sums. In this case, we are summing first A, then B, and then C. We select the first variable to be summed A, and what we are going to do is just group together only those factors that depend on the variable that we are going to sum out. In this case, this factor and this other factor. We multiply them together and we get an additional factor, which is going to be a function of these two random variables, A and B. Then sum out A in that factor, and we get a new factor that only depends on the variable B. The next variable to be summed out is B, and we do the same process. We group together the factors that depend on B, which would be this one, and the newly created factor resulting from summing out A. We multiply them together and get another factor that depends on the variable B and the variable C. We sum out B in that factor and get another factor that depends on C, and so on. In the end, the computational cost in this case, it scales as n to the square of n, because the largest factor that we are computing in this case depends only on two random variables. So by specifying an order in which we are going to do the computations, we can produce a very large savings in computational cost. And the main idea is that the graphical model expresses the joint distribution as a product of simple factors that depend on a small number of random variables, and we only need to compute some expressions once. And by catching the intermediate results, we avoid to generate those expressions many times. In this case, we have that this sum over A, we are storing the value of that sum in terms of the newly created factor that only depends on B. And that factor is then used to do the computations on B. In this case, we are recomputing that factor many times, which is useless. So this idea can be formalized in terms of an algorithm, which is called the sum product or variable elimination algorithm. This procedure basically does what I mentioned before. It receives an input, a set of factors, whose product specifies the joint distribution, a set of variables to be eliminated, to be summed out in this joint, and an ordering for those variables. And the method iterates, just selecting the next variable to be eliminated, and then eliminating that variable. So in this case, we had the ordering for the variables was A, B, and C, and the first variable to be eliminated was A. The elimination of the variable is done by that subroutine, which eliminates the variable. It just receives as input the current factors and the variable to be summed out. It groups together the factors that depend on the variable to be summed out in this set, phi prime, and then it multiplies together those factors. So in this first call if we call the sum product variable elimination with this ordering of the variables and the factors, the first set of factors, the first variable to be eliminated would be A, and the first set of factors, phi prime, would be this one and this other one. Then they are multiplied. The factors that depend on the variable to be eliminated, they are multiplied to create a new factor called the psi, And this factor is then marginalized with respect to the variable to be eliminated to create a new factor called tau. And the routine just returns the newly created factor tau and the previous factors. So in the first call to this method, according to this expression, the variable would return a factor that depends only on b and all the other factors that that don't depend on the variable that has been eliminated, a. Okay. Yeah. So when we observe when we observe some of the value of some of the variables, what we do in the joint, we just reduce the factors that depend on the observed variables, and we just consider those factors as a functions of the variables that are not observed, and we consider only the entries in those factors that agree with the observed value of the variables. So this is relatively easy. And if we are going to sum out variables, we won't consider the variables that are observed. So this is going to be a pseudocode of a method that allows us to do these exact marginalizations in a computationally efficient way. And we can see an execution of this algorithm for the following directed graphical model. In this case, we are interested in computing the marginal distribution for the variable j. The joint distribution would be this one, which can be written as a product of factors. So in this case, we would have to, the Bayesian network will specify a factorization of the joint distribution. We will have one factor for each node, which is going to be the conditional distribution of that node given the parents. So we will have a factor for C, which is shown here. We will have a factor for D given C, which is this other one. We will have a factor for the distribution of G given I and D, which is this other one. Another factor for H given G and J, which is this other one, for example. And this algorithm, variable elimination, can be applied to both directed and undirected graphical models. So we specify, if we want to sum out all the variables except j, what we do is we specify an ordering for summing out these variables. In this case, we have this ordering of the variables, and we call this sum product variable elimination algorithm. In the first step, we are going to eliminate the variable c. So we group together those factors that depend on this variable. In this case, there are these two factors only. We multiply them together to get a new factor psi. This factor, we will get a new factor that is the product of all the factors that depend on c, on the variable c, and we will sum out this variable. So this produces a new factor tau that only depends on the variable d. Would be this other factor that is the result of marginalizing the variables, the variable c. Then the next variable to be eliminated is the variable d. We group together again the factors that depend on that variable. In this case, we have this factor and the newly created factor tau 1. We multiply them together, we get a new factor psi 2, which depends on these variables g, I, and d. And we sum out in that factor d to create a new factor tau 2, which only depends on these two variables g and I. So tau 2 is created by, yes?
Sorry, in the joint distribution, the j variable is missing.
Yeah, this is a typo. Yes, that should be, yes. Yes, we should have an entry for j there. Okay, so we repeat this process until we sum out the last variable, and we get a factor tau 7 that only depends on the variable j, and this factor represents the marginal distribution for j. All these factors are going to be probability tables. There are going to be tables with one column for if these variables are with one column for each value of a random variable, and as many entries for the possible states of these variables. Okay, so we have this algorithm, variable elimination, and it turns out that we can get many insights about the computational complexity of variable elimination by interpreting this algorithm as doing operations in a graph which is going to be called the induced graph. In this graph, basically, we are going to connect two nodes whenever the two variables appear together in one of the factors of variable elimination. So we see all these factors that are used by variable elimination. It would be all these factors, the factors psi produced. In this table they are not included, but they would depend on these variables, and we have all the factors tau also. Whenever we have two variables that appear together in these factors, we will connect them in the induced graph. So this would be the induced graph for this execution of a variable elimination. And we can obtain this induced graph in a very easy process. This would be the graph for the directed graphical model on which we are summing out running the variable elimination. So to get the induced graph, what we are going to do is basically first obtain the undirected version of this graph. We are going to do this with this process called the moralization that we saw in the first lecture. Basically, what we are going to do is for each node in the graph, we are going to have a factor that depends on the node and the parents of that node. Because of this, we are going to connect all the parents in the node because they appear together in that factor. So in this case, we have that G has two parents, D and I, so we connect them. We have that the node J has two parents, S and L, so we connect them also. And we see that H has two parents, G and J, so we also connect these nodes. And then we eliminate the direction of the arrows to get an undirected model. So at this point, I'm just connecting those variables that appear together in a factor in the original directed model. So I haven't done any operation with variable elimination so far. Yes?
So why is there an edge between GNS and
So this is the final induced graph, which connects all the variables that appear together in a factor during the execution of variable elimination. At this stage, I haven't run variable elimination yet. So during the execution of variable elimination, I will be adding edges in this graph, and this will be one of the edges to be added.
The moralized graph is not all there?
No. So the moralized graph, you can understand variable elimination as doing operations in a graph, and the moralized graph is the first snapshot of the graph, and then during later executions of variable elimination, we will be doing operations on this graph. Basically, what we have to do is connect two variables whenever they appear together in a factor, and this basically means that whenever we are going to eliminate a variable in a variable elimination, we will basically multiply together all the factors that depend on that variable. For example, in this case, I am going to eliminate C, and I am multiplying together all the factors that depend on C. I'm producing a newly created factor psi that that is the product of all those factors, and this means that whenever I eliminate a variable, I'm going to get all the factors that depend on that variable and create a global factor that is the product of all those. This means that whenever I eliminate a variable in the induced graph, I will be connecting all the neighbors of that variable, because they will belong to, those neighbors will belong to factors that depend on that variable. They will be multiplied together, and they will form an expanded factor. One of these factors, psi psi produced during the execution of variable elimination. So the first variable to be eliminated is variable C. I should connect all the parents, all the neighbors of C. There is only one, so I don't have to do anything. The next variable to be eliminated is D. In this case, I have two neighbors, and they are already connected, so I won't do anything. The next variable to be eliminated is the variable I, and it has these two neighbors, G and S, so I will be connecting those two neighbors. And I am connecting them because if you see when I eliminate a variable I am multiplying these factors that contain the variable S and the variable G. I will create a factor psi that depends on those variables, and I should connect them. So I will add this edge. The next variable to be eliminated is variable H. So I have to connect all the neighbors of H, which are already connected. Then the variable to be eliminated is G. The variable G has neighbors I and let's see. Yeah, I don't know why it is not connected G in this case.
I think all of its neighbors are.
Sorry?
Oh, I think all of its neighbors are already connected. J and S.
Yeah, okay. So the idea in the induced graph is that we will be connecting all the neighbors, all the variables that appear together in a factor, and we will have that every factor produced during the variable elimination algorithm will be a clique in this induced graph. A clique was a set of fully connected nodes, and every maximal clique is going to be the scope of one of these factors, psi, produced during the execution of a variable elimination. So these factors, psi, are the product of are the largest factors produced during the execution of variable elimination, and they will correspond to a maximal clique in the induced graph. So if we have this is the induced graph, we have the maximal cliques in this graph, which have been highlighted with these circles. We have that CD is a maximal clique because it is fully connected, and we cannot add another node to this clique without it ceasing to be a clique. The same for all the other cliques. For example, this one, G, H, and J, is a maximal clique, and we have a corresponding factor, psi, produced during the execution of variable elimination. In this case, G, H, and J is just this factor, psi 4 would be the one corresponding to that maximal clique. So during the execution of variable elimination, we can construct this induced graph, and the largest factors produced in variable elimination will be maximal cliques in this induced graph. This means that the cost of running variable elimination is going to be exponential in the number of nodes in the largest clique of the induced graph. That is going to be the measure of the computational complexity of the cost of this algorithm. So the idea is that if we want to find an ordering of the variables that leads to a variable that leads to an execution of variable elimination with low cost, we should find an ordering that produces an induced graph with a small largest clique in the graph. So the thing is that the cost of variable elimination basically depends on the ordering of the variables. And if we want to find the optimal ordering, it's going to be a very difficult problem. It is an NP-hard problem. So the idea is that instead of trying to solve that problem, we will use a heuristic method. And we can just use a heuristic method based on the induced graph. Basically, the operations in the induced graph basically summarize the evolution of variable elimination. And at each point, during the execution of variable elimination, when we have to select a new variable to be summed out, what we are going to say is have a look at the current snapshot of the induced graph, and then select the variable that satisfies some rule, like that minimizes some heuristic. Like, for example, if you have to eliminate a variable, have a look at the current version of the induced graph, and then add the variable such that when I eliminate that variable in the induced graph, it will create the smallest number of connections, for example. That could be a heuristic to try to find a good elimination ordering that has low computational cost. So that's the induced graph. Another property of the induced graph is that we won't find any loop in this graph with a size larger than 3. The reason for this is that because of the product of factors, we are, during the execution of variable elimination, we are multiplying the factors that depend on a particular random variable whenever we are eliminating that variable. And that process will basically eliminate any loop larger than 3 in the final induced graph. So, okay, we have this algorithm, variable elimination, that allows us to sum out variables in a computationally efficient way. This algorithm can also be interpreted as operating on a structure which is called a click tree. Basically, the execution of variable elimination defines a click tree. This is a tree that satisfies that has these properties. We will have a node for each of the factors produced by variable elimination. Of these factors, psi I. In this case, we were producing 7 factors, psi I, one for each variable that we were eliminating. So in the click tree, we are going to have 7 nodes, one for each of these factors, psi I. And each node is going to be associated with the variables that are in the scope of the corresponding factor. So the first factor, psi 1, depends on the variables C and D. So we have associated in the first node the variables C and D. And the fourth factor, psi 4, in this case depends on the variables H, G, and J. So we have those variables associated in that node. Finally, when we have these nodes in the click tree, we will have connected 2 nodes whenever the corresponding factor tau produced during the execution of a variable elimination, whenever we will connect nodes I and J when tau I is used to compute tau J. So if this is the execution of a variable elimination, we have that to compute tau 2, we are using the factor tau 1. And to compute tau 3, we are using the factor tau 2. So we connect the nodes 1 with 2 and 2 with 3. Then we have that to compute tau 5, we are connecting the factor tau 4. We are using the factor tau 4 and tau 3. So we connect the nodes 3 and 4 to 5. And the same for tau 6, we are using tau 5, and tau 7, we are using tau 6. So we connect those nodes. This click tree will also have associated with each link a set of variables which are called the SEP set for that link. And it is just given the intersection of the variables associated with each node. In this case, we have the variables C and D and G, I, and D. So the subset is just the intersection. In this case, we also have that it is the intersection, and for example, in this case, we have J and L and S. The intersection is J and L. Okay, so this is the click tree produced by the execution of variable elimination, and we will see that variable elimination can be seen as operating on this click tree. In particular, we can see that we will see that variable elimination will be interpreted as passing messages in this click tree. The click tree will also have these properties. The click tree produced by variable elimination. It will have the running intersection property, which says that for any variable that appears in two nodes, we will have that that variable will be present in any additional node that is in the path connecting those two nodes. This running intersection property originates because if we see that some variable appears in some of these, if some variable appears for the first time in one of the nodes, it means that that variable is in the factors psi I produced during the execution of variable elimination. Those factors will produce another factor, tau, that is the marginalization of that factor psi. And this means that if we have a variable present in one of the nodes, that variable will be propagated forward in the tree, or it will either disappear because it is being summed out. So that's why the nodes will satisfy this running intersection property. Whenever a variable appears, it is propagated forward because we are connecting nodes using the factors tau, and the factors tau will contain the variable if it is not summed out, and it will be propagated forward the variable across the tree unless it is summed out. This running intersection property is satisfied by this click tree. We can see it, for example, if we have a node here that contains the variable j, here we have another node that contains also the variable j, and any intermediate node in the path connecting these nodes contains the variable j also. Another final property of the click tree is that is the family preservation property. Each factor in the original distribution will be associated with a node that, such that the variables in the scope of that factor, the variables on which that factor is evaluated, are contained in the set of variables associated with that node. So in this click tree, we have that each factor in the original distribution is used to produce one of the factors psi. We have that any factor in the original distribution is used at some point to produce the corresponding factor psi. So basically each factor in the original distribution will be associated with the node that corresponds to the factor psi that is computed using those original factors. So we have these click trees, and it turns out that basically variable elimination can be interpreted as passing messages in a click tree, and it can be also implemented as just doing message passing in a click tree. So basically we can see that we can interpret each of these factors tau as a message that is passed from one node to another. And basically each node, the operation that it does is it gets the factors associated to that node, the factors phi associated to that node. It multiplies them by the incoming messages. In this case, this is the first node. Sorry, this is the first node. There are no incoming messages in this case to that node. And it creates a new factor tau1, which is going to be a message that is passed to the second node. The second node multiplies that message by the factor phi associated with that node and creates a new message, and so on. So the whole idea is that variable elimination can be interpreted as a message passing in the click tree. Basically, by the family preservation property, we will have a factor assigned to each node in the click tree. We will denote by alpha phi the node associated with that factor. And for each node, we will create a potential, an initial potential for that node, which is the product of the factors phi associated with that node. And then we define the messages. The messages are just the product of the factors phi times the incoming message to a node, and then we marginalize with respect to the variables that are not in the subset of the link that is used to pass the message. So in this click tree, basically in this first node, we are multiplying the factors to send the message. We are multiplying the factors associated with that node, these two. Then we are marginalizing with respect to the variables that are not in the subset, which in this case is variable C. And then we are sending the message. The message is the node, the factor tau. So once we do this message passing across the links in the graph, and then for each node we can define the belief, which is the product of the initial potential associated to the node and all the incoming messages to that node. It can be shown that that is just the marginal of the joint with respect to all the other variables that are not contained in the subset of variables associated to the node. This means that to compute the marginals, we only have to do message passing and then compute these beliefs in the nodes of the click tree. Basically, if we want to compute a particular marginal for a random variable set j, we would follow the following steps. We select a node in the click tree that contains that variable. We do the message passing and compute the belief in that node, and then we just marginalize the belief with respect to all the other variables that are not set j. So let's see how we can do this in a particular click tree. So given a probabilistic graphical model, we assume that we have a click tree for that model, and then we can do this message passing. If we want to compute the marginal of j, what we can do is select a node that contains that variable, and then do message passing. This is a click tree for this graphical model. It satisfies the it satisfies the family preservation property. It has, for each node, it has associated a set of factors in the initial distribution, and it satisfies the running intersection property. It can be seen that this click tree satisfies this running intersection property. So we can do message passing to compute any marginals in this click tree. So if we want to compute this marginal, we select a node that contains that variable, for example, the node 5, and then we do message passing. We will select that node as a root of the tree, and then we do message passing from the leaves to that root. So this would be shown here. We have selected 5 as the root of the tree, and then we do message passing from the leaves, from this node to the second node, the third node, and to node 5, and then from the fourth node to node 5. The message sent from each node is just a product of the potential, initial potential associated to that node, marginalized with respect to the variables that are not in the subset. In this subset, we have the variable d, so we marginalize the initial potential with respect to c. In the second node, the message that we are going to pass is just a marginalization of the product of the initial potential associated with that node, psi 2 in this case, which is just this factor, times the incoming message from the first node, and then marginalized with respect to the variables that are not in the subset. In this subset, we have the variables g and I, and the variables that are not in that subset is the variable d. So we do this until we get to the root. When we get to the root, we have all the incoming messages, and to compute the marginal, we just multiply those messages times the initial potential associated with that node. We would multiply the message 3, 5 and the message 4, 5 times the initial potential, which are these factors, and we obtain that belief for that state, for that node, which is a factor that depends in this case of 4 variables, and we can use that to compute the marginal. We only have to sum out all the other variables except j in in that factor given by the belief. Okay, so the advantage of using the click tree is that we can compute all the marginals in a particular graphical model by just with the cost of doing 2 executions of variable elimination. For this, we only have to pass all the possible messages in the graph. And this can be done very easily by just picking a random node as the root, send all the messages from the leaves to that root. Once we have in the root all the incoming messages, we then send all the messages, all the possible messages from that root to the leaves again. And that guarantees that for each link in the click tree, we have all the possible messages, the messages that go in one direction and in the other direction. For each node, we can compute the beliefs for each of the nodes in the click tree, and then each node will have the marginal over the variables in its scope. This is an example. We select 5 as the root, we send all the messages from the leaves to the root, and then we send all the messages from the root to the leaves. And this allows us to compute all the marginals with only twice the cost of variable elimination. So we have seen that variable elimination can be interpreted as doing message passing in a click tree. The problem is how do we get this click tree? And one possibility is we have seen that just a single execution of variable elimination produces a click tree. But there are other ways to obtain a click tree. For example, from a chordal graph, which is going to be just one of the induced, it's going to be an induced graph that could have been generated during the execution of variable elimination. A chordal graph is just a undirected graph with no loop larger than 3, and all the induced graphs will be a chordal graph. So in this case, we can obtain a click tree by doing these steps. We obtain the undirected graph by doing this moralization. It was the same that we did to construct the induced graph. And then we obtain a chordal graph by triangulation. We will basically eliminate any loop larger than 3 in that graph. We will get a graph that could have been an induced graph produced by the execution of variable elimination. And in that graph, we will find the maximal clicks in that triangulated graph. And we will just make each node in the click tree correspond to one of the maximal clicks in the chordal graph. So basically, during the execution of variable elimination, we obtained an induced graph which does not have any loop larger than 3. And each of the maximal clicks in that induced graph corresponding to one of these factors psi 1 to psi 7 produced during the execution of variable elimination. And those factors were the ones used to construct the nodes in the click tree. So we can do that, just that by creating an induced graph by just breaking any loop larger than 4, finding the maximal clicks in that graph, and then those clicks will be the nodes in the induced graph. Once we have the nodes in the will be the nodes in the click tree. Once we have the nodes in the click tree, we only have to connect them to form a tree, and we can do that by just finding the maximum spanning tree with in which we weight each connection by the number of common variables between the 2 nodes connected by that edge. So we obtain a click tree, and it will turn out that the computational cost of doing message passing in that node, doing message passing is the same as running variable elimination. It's going to be exponential in the size of the largest click in that graph. It was the same as in the execution of variable elimination. In the execution of variable elimination, we had that the cost is exponential in the number of nodes in the largest click of the induced graph. And when we construct a click tree, the cost of doing message passing in that click tree is going to be exponential in the number of nodes in the largest in the number of variables associated to the largest node in that click tree, which will correspond to one of the clicks in the induced graph, of the largest click in the induced graph. So the idea is that if we want to have a click tree in which we can have a low computational cost of message passing, we would like to find a triangulation that generates a largest click which is small. Again, this is finding that triangulation is going to be an NP-hard problem, and the alternative is to use some heuristic method in the same way that we were selecting and ordering for the variables to be eliminated during the execution of variable elimination. We can also use a heuristic method to do the triangulation. Yeah, so let's have a look at an example. How do we construct a click tree for a particular graphical model? This shows a hidden Markov model for 4 variables that have a temporal dependence. We are using a hidden state that captures the temporal dependencies among the variables, and each variable is conditionally independent of all the others given the state. So to obtain a click tree, what we do is these steps. We obtain an undirected graph by moralization. The corresponding undirected graph in this case is this one. We basically have to marriage all the parents of each node. In this case, each node has a single parent, so we don't have to do any marriage. And we eliminate the direction of the edges. So we get this undirected graph. We then find, we would have to do a triangulation of the graph to eliminate any loop larger than 4. There are no loops larger than 4 in this case, so we don't have to do this step. And then find the maximal clicks in the resulting graph. So the maximal clicks in this graph, we have that each pair of 2 nodes is a maximal click. We cannot add any other node to any pair of nodes without the resulting graph ceasing to be a click. So if we have these 2 nodes, Z1 and X1, we cannot add Z2, for example, without the 3 nodes still being a click. So one of the clicks, maximal clicks, is this one, X1, Z1, Z1, Z2, Z2, Z3, and so on. And then we would connect the nodes by finding a maximum spanning tree with a weight given by the number of common variables between the 2 nodes connected by each edge. So in this case, all the edges have weight 1, and we just select a maximum spanning tree for the nodes, and we obtain a valid click tree. So we have seen that exact inference, the cost of exact inference depends on the size of the largest click in the click tree, which is often called the tree width. And basically, if the tree width is very large, doing exact inference is going to be intractable. So the question is what to do in this case. In this case, we can do some approximate inference. Instead of doing exact computations, we can say, okay, I can afford to do some approximations, and at the cost of, I will do some approximations that with the advantage of reducing the computational cost. So in this case, we will construct an approximate distribution to the target distribution. So if we want to compute the marginals, I'm going to say, okay, I don't want the exact marginals. I can work with some approximation to these marginals. To do this, this approximation can be obtained by selecting a form for this approximation to the marginals that will be adjusted to the exact marginals. For example, I can say, if I am interested in the marginal distribution of these 2 variables, Z1 and Z2, I can say, okay, instead of working with the exact marginals, I can say I'm going to assume that the marginal distribution of Z1 and Z2 factorizes. and I will try to find the factorized distribution that best matches that marginal. So another possibility is to draw samples from the exact distribution, and then approximate construct the approximation using those samples. So we'll see that in the first case we will have to optimize the approximation to match the target distribution, and some of these methods can also be viewed as doing message passing on a graph. This is the case of loopy belief propagation, which is a version of this message passing algorithm that I described before, but we are going to do the message passing instead of in a click tree. We are going to do it in a cluster graph, which is going to be similar to a click tree, but it is going to contain loops and cycles. And because of these loops, the result given by the message passing algorithm, it won't be exact, it's going to be approximate. So a cluster graph is just like a click tree, but with no cycles or loops. And we have that in this case the links between two nodes. We will have groups of variables associated to each node, but the links in this case can be a subset of the intersection of the variables. In the click tree, we had that the subset, basically the variables associated with each link, is just the intersection of the groups of variables. In the cluster graph, it is just a subset of the intersection. This cluster graph will have to satisfy the family preservation property, the same as in the click tree, and a generalized version of the running intersection property. This generalized version says that for any two nodes containing a variable, we have only one path connecting those two nodes, such that X belongs to all the subsets in that path. So I have two nodes in the cluster graph that contain a variable. I only have one path, such that all the edges in that path contain that variable. Yeah, so we will do message passing in this cluster graph in the same way as before. So let's have a look at a particular example where we have a probabilistic graphical model, and we can obtain a click tree and a cluster graph. In this case, we have a distribution which is given by the product of these four factors. The corresponding graphical model is this one. We can obtain a click tree for this graphical model following the steps that I mentioned. We have to moralize this graph. It is already an undirected model, so we don't have to do any moralization. Then we have to eliminate any loop larger than 4. We can do that by just adding a link between B and D, and we eliminate those loops. And then we find the maximal clicks in that graph. The maximal clicks are going to be, if I add a link between B and D, are going to be A, B, and D, this one, and then B, C, and D, this other one. I connect the two nodes using with a subset which is the intersection of the variables, and then I can associate one of these factors to each node. To the first node, I will associate the factor phi1 and the factor AD, which is phi4, and to the second node, I will associate the factor BC and the factor CD. I can do message passing in this click tree. If I do message passing in this click tree, the cost is going to be exponential in the size of the largest click, which in this case we have 3 random variables. If the random variables can take n different values, we will have a cost that is n to the 3rd power. We can also obtain a cluster graph. This shows an example of a cluster graph for this probabilistic model, where we have different nodes with variables associated to those nodes. We will have, for each node, we will associate a factor. In this case, for the first node, we have the factor phi1. For the fourth node, we have the factor phi4, and so on. And we will have some subset for each node that is a subset of the intersection of the variables contained in the nodes. So the question is, yes.
So can you, I'm a bit lost, but what's the point to split up the factor ABD into two factors, AB and AB, and similarly?
So the idea is that doing a exact inference in this, working with this click tree, I can do exact inference, but it depends on the size of the largest click in this graph, which depends on 3 variables. If I split the factors, the largest factor which I will be using depends only on 2 variables. That's why working with this cluster tree is going to be less expensive than working with the click tree, because the nodes, they include only 2 variables. And yeah, that's it. That's the advantage of working with a cluster graph.
And the stopping rule, when, for example, I have like big factors, and is there like always, do I have to reduce the size to of 2, or do I sometimes say, okay, I can manage the size? And
so that's something you have to choose, and you will get a balance between the computational cost of operating with the cluster graph and the accuracy of the computations. So if you have a cluster graph that is similar to the click tree, you will have a larger cost, and the simpler that the cluster graph is, the lowest the computational cost. We will see how to select a particular cluster graph that leads to low computational cost in the following slides.
What exactly doesn't make B a cluster graph?
B, what do you mean by B? This figure, a cluster graph.
Yeah.
So it would be that so this is a tree, and the cluster graph in general it won't be a tree because it will have loops.
But I guess that every cluster graph is the cluster tree.
You can say that a cluster graph that is a tree, it would be a click tree.
So every click tree is a cluster graph?
Yes.
Okay.
Yes, it is a cluster graph with no loops.
Okay.
So how do you choose the cluster graph? So to do this, you will have to find a balance between the computational cost and the accuracy that you want, and doing message passing in clusters graphs that leads to more accurate results will be more computationally expensive, and vice versa. So the chosen cluster graph should also satisfy these properties, the running intersection property and the family preservation property. So a typical solution to choose for the cluster graph for a particular problem is the Bethe cluster graph. And the construction of this cluster graph can be easily automated. We just create 2 layers of nodes. In one of the layers, I'm going to have a node for each factor in the factorization of the joint distribution. And then I will have also a layer of small nodes that contain all the variables, all the different variables. And I will basically connect the large nodes with the small nodes whenever they share variables in common. So let's see this for a particular example. We have a joint distribution that factorizes as the product of these factors. I have 2 layers of nodes, one layer which contains 1 node for each factor, and then another layer that contains 1 node for each random variable in the joint. And I just connect the 2 nodes, 1 node from the 1 large node with all the small nodes that correspond to variables contained in the large node. So if I have in the large node, I have in this case the variables A, B, and C. Then I'm connecting a variable, the small node A, B, and C. And in this case, I have the variables D and E, so I'm connecting it with D and E. These large nodes have associated factors. One factor have as associated factor one of the factors in the joint, but these small nodes, they won't have any factor associated. They will have a factor which is constant and takes value 1. So this Bethe cluster graph is guaranteed to satisfy this the running intersection property and the family preservation property, and it will allow us to do efficient